Hello everyone, welcome to another lesson in Theory of Structure. I am Engineer JC and I am going to discuss to you the application of influence line. So in our previous video, I taught you how to draw the influence line of a beam. I have posted the discussion. I have posted the link of that discussion in the description below. And in this lesson, we will try to apply the influence line in solving the reactions at any point in a beam using influence line diagram with given dead load, concentrated and uniformly distributed live load. Okay, so let's begin the discussion. So we will go directly with an example. So I have this example here. For the beam shown, determine the maximum positive and negative shears and the maximum positive and negative bending moment at point C due to a concentrated live load of 90 kN, a uniformly distributed live load of 40 kN per meter, and a uniformly distributed dead load of 20 kN per meter. So in this example, we will try to solve the maximum positive and negative shear and also the maximum positive and negative bending moment with a given live load and uniformly distributed live load and a dead load. So we have this example. So by the way, if you missed to watch my discussion on how to draw the influence line by two methods, we have a static and the Muller-Breslau's principle. I have also posted the link in the description. Please watch them before watching this video so that you will be able to follow my discussion. Okay, so the first thing we do here is of course draw the influence line of shear at point C. Okay, so we cut at C. So if we cut at C, we would have a shear on the left side of C and shear just to the right of C. So we would have this one. So we would have this one. We have a shear or SCL, let's say that is shear just to the left of C and shear just to the right of C. So in other book, this represented by V. Okay, and we have also a vertical reaction at B, so we have dy, and a vertical reaction at D, which is dy, and we know that when we have a hinge support, we should have a 2 reaction, and that is we also have dx here. But since we are dealing here with vertical load, so we may assume that dx is equal to 0. So in order to create an influence line, so we have to place our unit load first at point A when our x is equal to 0. So again, we have a two approach in drawing the influence line. So this is by using static or by equilibrium equation. So later we will also try to solve the influence line using the Muller-Breslau's principle. Okay, so when we place our 1 kilonewton or 1 unit load at A, so when our x equal to 0, then we compute for the shear just to the left of C and shear just to the right of C. So we have to first sum up a moment at D to compute for the reaction. So we have by times the moment arm, a 9, that is the distance from D. This is negative since this rotates clockwise with respect to D. And then we have a plus 1 unit load times the moment arm from D is 12. Okay, and this equals to 0. So we have by here equals to 4/3. And for dy, we have to sum up force vertical is equal to 0, upward force are positive. So we have by plus dy minus 1 is equal to 0, but by here is 4/3 plus dy minus 1 is equals to 0. So we have dy is equal to negative 1/3. Okay, so since our goal here is to draw the influence line of shear at C, then we need to draw the SCL and SCR when our 1 unit load is at point A. So by looking at the cut section, we know that by here is 4/3 and dy is negative 1/3. So we can compute for SCL and SCR separately here. Now, in creating an influence line diagram of shear point or shear of the point along the beam other than the reaction, according to the rule, if our 1 unit load is on the left side of C, then in drawing the influence diagram, we should consider the free body diagram on the right side of C. Okay? But if our 1 unit load is on the right side of C, then we consider the free body diagram of the left side of C. Okay? So in this case, since our 1 unit load here is on the left side of C, then we will be looking at the free body diagram of the right side of the C. So basically, we will consider the free body diagram of C to D. Okay, so we have C to D here. So since we know that we have the value of our dy here is as 1/3, so therefore we have summation of forces vertical is equal to 0, upward or positive. But anyway, but before that, we should always use the sign convention that we usually used. So for the left shear, our convention here should be downward shear force. Now for the right shear, it should be going upward. Now, in this case, we have SCR minus dy is equal to 0. So we have SCR here minus 1/3 is equal to 0. So we have SCR is equal to 1/3. So therefore, our SC is equal to 1/3. So we can say then that when our x is equal to 0, our SC is equal to 1/3. And then we move our unit load at point B, okay? And that is when our x is equal to 3. So at point B, we would have a new values of by and dy. So we will again compute the forces or reactions at two support. So we will assume that all the reactions are going upward. So we can use summation of moment at D is equal to 0. Counterclockwise or positive. So we have by times 9, and this is negative, plus 1 times 9, and this equals to 0. So we have a by here is equal to 1. Now then, sum up forces vertical is equal to 0, upward force are positive. So we have by plus dy and minus 1 is equal to 0. So we have here 1 plus dy minus 1 is equal to 0. And this gives us dy is equal to 0. So when we placed our load at exactly point B, or at x equal to 3, then we have the value of our by, which is equal to 1, and the value of dy, which is equal to 0. So since our 1 unit load is still on the left side of our C, so we will be considering the right free body diagram. So we will again consider the section C to D. Okay, so in this case, we sum up forces vertical is equal to 0, upwards forces are positive. So we have SCR plus dy is equal to 0. So since we have 0 SCR, so we know, but since we have a 0 dy, so therefore our SCR here is equal to 0. So this would be the value of the shear at C. Okay, so therefore we have SC, or the shear at C, is equal to 0 when x is equal to 3. And then we move our 1 unit load at exactly point C, and that is when our x is equal to 6. So we compute for SC. So we solve all the reactions. So we have to sum up moment at D. This equals to 0. So counterclockwise positive. So we have by times 9. That is negative, plus 1 times 6 is equal to 0. So we have by here is equal to 6 over 9, or this is 2/3. Okay, so this one is 2/3. And for dy, we just need to sum up force vertical, and all the force acting upward are positive. So we have by plus dy, then we have 1, okay, that's minus 1 is equal to 0. And since our by here is 2/3 and dy here is unknown, so minus 1 is equal to 0. So this would give us the value of dy, which is equal to 1/3. So we have our dy here, which is 1/3. Now take note, at x equal to 6, we will have 2 ordinates at that point. And that is when our shear on the left and ordinates on the right side of the C. So to compute for the ordinates on the left side of the C, then we consider again the right free body diagram. So we consider again C to D. So we will be putting our 1 on the left side of our C. So that means we have summation of forces vertical is equal to 0, upward force are positive, and then we have here S CR plus dy is equal to 0. SCR is 1/3, so we have plus 1/3 is equal to 0. So we have SCR is equal to negative 1/3. So therefore, the ordinates on the left side is equal to negative 1/3. And this is our, again, ordinates on the left side of our C, of point C rather. Now, we place 1 Newton at point C, but in this time, we put our 1 unit load just to the right of our C. But since our 1 unit load is still on point C, so we will be having the same value of reaction. So we have 1/3 for dy and 2/3 for by. But in this case, we will be computing for the ordinates on the right side of our point C. So we will be considering the free body diagram on the left side. So, and that is from A to C. So in this case, we sum up forces vertical is equal to 0. Upward force are positive. That means we have by minus SCL is equal to 0. So we have by is 2/3 minus SCL is equal to 0. So we have shear to the left of C is equal to 2/3. So therefore, the other coordinates for the shear at point C is 2/3. And this 2/3 here is on the right side free body diagram, or right side ordinates. So we move our 1 unit load at point D, and that is when our x is equal to 12. Okay? So we will have new value of reactions. Our 1 Newton here is on point D, or at the rightmost support. So basically, to compute for the ordinates on point D for our reaction at C, so we will be considering here the left side free body diagram, since our 1 unit load here is on the right side of our point C. So again, we will be considering the left side free body diagram. So in this case, we need to compute first the reaction, so we can sum up moment at D is equal to 0, so counterclockwise positive. So we have by times 9, and this equals to 0. So we have by is automatically equal to 0. And then if we sum up force vertical, all force upward, so we have by plus dy minus 1 is equal to 0, but we know by is 0. So therefore, we can say that dy is equal to 1. So we have dy here is equal to 1 and by equals to 0. So we now proceed to the computation for the ordinates at point D. So we will be considering the left free body diagram. So we can sum up force vertical is equal to 0. So we have by minus SCL is equal to 0. So that means we have 0 by. So therefore, we can say that our shear of the left of C is equal to 0. So therefore, the shear at C when our 1 Newton load or 1 unit load is at point D is equal to 0. So these are the ordinates of our shear or our influence diagram with respect to the value of our X or to the placement of our 1 unit load. So let's now proceed to the drawing of the influence diagram. When our X equal to 0, our shear is 1/3, so that is positive, so that is upward. And when our X equal to 3, we have SC is 0. And for our X equal to 6, we have SC is negative 1/3 and SC is 2/3. So we have negative 1/3 and 2/3. And for X equal to 12, we have SC here is 0. So we connect the dot. So we have here the influence line for shear at C. Okay? Now if we use the Muller-Breslau's principle, so since at C we have downward and upward shear, so we have SC on the left and SC on the right. So if we let this beam deflect, so we would have this one, and the total deflection at point C is 1 unit. And this deflection here is similar to our influence line. So basically, if this is our deflection due to the shear at both sides of our point C, so therefore this would also be our influence line diagram. Now we do not know yet the ordinate at this point and this point as well. So in this case, we have to compute the reaction at B and reaction at dy. So basically, we need to apply equilibrium equation at this. If we have our 1 unit load at point C, we would have the value of by here equals to 2/3 and the value of dy here is equal to 1/3. Again, to determine the ordinate of point C just to the right of that location, we need to consider the free body diagram of the left. But if we want to determine the coordinate to the right side of point C, then we need to consider the free body diagram of the left side. So in this case, we have this SCR. So to determine the ordinate at this point, so basically we just need to consider dy, since that is dy here is basically located on the right side of our C, and this ordinate here is referring to the left side of the C. So therefore, our ordinate here is equal to 1/3. Okay, and this one is negative. Now for the ordinates just to the right side of the C, so we will be referring to the free body diagram on the left side of our C. So in this case, we will use SC to the left, which is equal to by, and that is we have a 2/3. So therefore, we have ordinates here is equal to 2/3. Now, we know that at point T, this one is support, so therefore, we do not have movement at that point, so therefore, this is 0. And at point B is 0 as well because that is restricted to move. But at point A, now we know that they have point A and point C has the same distance from point B. We have 3 and 3 respectively. So therefore, our ordinate here is the same. That is 1/3. So in applying Muller-Breslau's principle to this beam, we need to apply equilibrium or static equation at the same time. So that's how you are going to use the Muller-Breslau's principle to this shear or to this influence diagram. And then we compute or we draw the influence line for the bending moment at point C. And now for the influence line for the bending moment at C, so we can use Muller-Breslau's principle directly. So if you want to solve it by equilibrium or by statics, you can do so, but to expedite the process, so I preferred to use the Muller-Breslau's principle. So in Muller-Breslau's principle, so we draw a moment counterclockwise to the left side of C and clockwise on the right side of C. So to release point C, so basically we would have this deflection. Now this released structure of our beam would also be our influence diagram. So this would be our influence diagram for the moment at C. But we do not know yet what would be the ordinates at point C, ordinates at A. But at point B, we are sure that this one is 0, and at point D is 0 as well. So how are we going to determine the ordinate at point C? Now take note, this is different from the influence diagram for reaction, because we know that if we released the point at which we want to consider, the movement of point is equivalent to 1. But for moment, this should not be equal to 1. Okay? So you need to compute the ordinate at this point by equilibrium. So if we put our 1 unit load at C, so basically we can compute the reactions at dy and by. So we have summation of moment at D is equal to 0, counterclockwise positive. So we have by, this is 1 is negative, times 9, plus 1 times 6 is equal to 0. So we have by here is equal to 2/3. Now to compute for the moment at C, when our 1 unit load at point C, so we cut at this point, okay? We have by and we have a moment C, so we have a direction of counterclockwise. So the distance is 3 meters. So we know that by here is 2/3. So we sum up moment at C is equal to 0, counterclockwise positive. So we have here 2/3 times 3. This one is negative because it rotates clockwise with respect to C. Plus MC is equal to 0. So we have MC here is equal to, we can cancel 3. MC is equal to 2. So therefore, when X is equal to 6, or when our 1 unit load is at point C, so our MC is equal to 2. So that would also be the ordinate at point C. So again, we can't be sure that at point C, the deflection is 1 unit. Okay, so we have to consider using statics or equilibrium equation. So therefore, the unit here is 2. Now, by ratio and proportion, we can also calculate the ordinate at point A. So we have, since we know that this one is 3, and this is 3 as well, so we have a relationship 2:3 is equal to, let's say this is our y. So y is to 3. So that means our y is also equal to 2. So therefore, the coordinate at this point is 2 as well. So this would be the influence diagram of the moment at C. Okay, so we use Muller-Breslau's to expedite the process. But the real question here is to compute the maximum positive and negative shears when you have a concentrated live load of 90 kilonewton and a uniformly distributed live load of 40 kilonewton per meter and a uniformly distributed dead load of 20 kilonewton per meter. So basically, our 20 kilonewton per meter here is acting all throughout the beam. So this one is 20 kilonewton per meter. But we know that 90 kilonewton concentrated live load and 40 kilonewton per meter uniformly distributed live load is changing its position. Okay? Unlike sa dead load, in which dead load we know this is acting all throughout the beam. So our goal here is to know where should these live loads be placed in order for us to come up with a positive or with a maximum positive and maximum negative shear and maximum positive and maximum negative bending moment. In order for us to come up with a positive or a maximum shear due to a concentrated load, we place that load to the point where the location of the highest ordinate. So in this case, we know that the highest ordinate is 2/3, in which this one occurs at point C. So therefore, we know that we locate our 90 kilonewton load here at point C. Okay, so we place 90 kilonewton at this point is our 90 kilonewton. And now to compute for the maximum positive shear due to the uniformly distributed live load of 40 kilonewton per meter, we place this uniformly distributed live load all positive area under the influence diagram. Now in this case, the positive area are within or between A and B and C and D. So therefore, we place our 40 kilonewton per meter on section or in beam AB. This one is 40, and on C to D. So this one is 40 kilonewton per meter. So we compute the shear generated by each load. So we have shear maximum at C due to the concentrated load 90. So we have 90 times the positive ordinate, we have a 2/3. This would give us 60. So this is the maximum positive shear due to the 90 kilonewton concentrated live load. Now, the maximum shear at C due to the uniformly distributed live load 40, you just need to multiply the load with the area under the influence diagram. So we have here 40 times 1/3 times 3. Okay, that's the length, times 1/2. Again, this one is the area of this region. Then plus 40 times the area of the triangle again for this region. So we have a 1/2 times the height 2/3 and the base 6. So this would give us 100 kilonewton. Okay? And due to the dead load, so we have shear maximum at C due to the dead load. Now since we know that dead load is acting all over the beam, so we need to add all the areas, whether that is positive or negative. So we have here 20 times the positive area, we have 1/2 times 1/3 times 3. So this area here. Then plus 20 times 1/2 times, now that is negative 1/3, that is the height of this triangle, times the width, which is 3, plus, now for this region, so we have 20 times 1/2 times 2/3 times the base, which is 6. It's again, this is 6, and this is 3, and this one is also 3. So we have the maximum shear at C due to the dead load, which is 40 kilonewton. So meaning, we have the maximum shear at C, or the maximum positive shear at C, that is 60 plus 100 plus 40. So therefore, we have 200 kilonewton. So due to the live load and dead load, this would be the maximum shear at point C. And next question is to compute for the negative shear at point C due to the concentrated live load and uniformly distributed live load and the uniformly distributed dead load. But since our dead load is acting all over the beam, so therefore we have the same position of our dead load. But for our concentrated load, since we are now asking for negative or maximum negative shear, so we need to reposition our load. Now in this case, our uniformly distributed live load should be placed under the negative area, or the negative area under the influence diagram. So in this case, we put our live load between B to C because this is the location of the negative area. So we have our live load at B to C. So this one is 40 kilonewton per meter. Now for the concentrated live load, so we place the concentrated load at the highest negative ordinate in our influence diagram. And in this case, we have the highest negative ordinate, which is negative 1/3. So we placed our 90 kilonewton here, the same as with the previous one. So we place it at point C. So we have 90 kilonewton concentrated live load. So the same procedure to compute for the negative maximum shear at C due to the concentrated live load. So we have 90 times, that is negative 1/3. So we have here negative 30 kilonewton. Now for the negative maximum shear at C due to the live load 40 kilonewton meter, so we just need to multiply 40 kilonewton and the negative area under the influence diagram. So this area here, so we just multiply it by 1/2 times negative 1/3, that's the height, times the length 3. This would give us negative 20 kilonewton. Now, for the shear at C due to the dead load 20 kilonewton per meter, so that's still the same. We have already computed that one, that is 40 kilonewton. Now, to compute for the negative maximum shear at C due to the load, so we just need to add. We have negative 30 minus 20 and the dead load, which is 40 kilonewton. So that means we have the negative maximum shear at C, which is equal to negative 10 kilonewton. So this one is our answer. Okay? So this is the maximum negative shear at point C due to the loads that we have. Now for the next question, we are asked to compute the maximum positive and negative bending moments at C due to the same loads. So to compute for the positive bending moment at C, so we place our 90 kilonewton concentrated live load here at the highest positive ordinate. Okay? But in this case, we have our highest ordinate here at point C, which we have here 2. So we placed our 90 kilonewton at point C. Now for the dead load, as we all know that dead load is fixed in our beam, so we have that is acting all over our beam. So we have 20 kilonewton per meter. Now for our uniformly distributed live load, which is 40 kilonewton per meter, so the same procedure with the shear one. So we place our uniformly distributed live load here under the positive area under the influence diagram. Now in this case, this is our positive area. So that means we place our uniformly distributed live load between B and D. So we have from B to D as the location of our live load 40 kilonewton per meter. So we have to compute the moment due to each load. So we have for 90, we have 90 times 2. This would give us 180 kilonewton meter. Now for live load, we have here 40 times the area, in which we have 1/2 times 2 times 9. This is the area of the entire triangle. So this would give us 360 kilonewton meter. And for the dead load, we have 20 times, since we have negative ordinate, -2 times the 3/2. Then we have a plus 20 times the area of the largest area. We have 1/2 times 2 times 9. This would give us 120 kilonewton meter. So to sum it up, that would give us the maximum moment at sea, or the positive maximum moment at sea, which is 180 plus 360 plus 120. This would give us 660 kilonewton meter. Now for a negative moment, so we reposition our live loads. So we put our concentrated load at the highest negative ordinate. So we have -2 here, so we placed our live load at this point. So we have this -90 kilonewton. And our uniformly distributed live load on the negative area under the influence diagram, which is from A to B. Okay, this one. So we have this area here, and this one is 40 kilonewton meters. So in this case, we compute the moment generated by each live load. So we have for 90, we have 90 times -2. This is -180 kilonewton meter. Now for live load, we have 40 times the area of this triangle, which we have 3 as our length, and that is we have 1/2 times 3 times -2. This would give us -120. Now we should not forget the dead load here, which is 120 kilonewton meter. So to sum it up, we have the negative maximum moment at sea, which is equal to -180 minus 120 plus the dead load, we have 120. So therefore, the maximum moment at sea is equal to -180 kilonewton meter. So this is our answer as the negative maximum moment at sea, and this is our answer for the positive maximum moment at sea. So by using influence diagram, we know how to or where to put or place or our live load, so that we will be able to determine which point or which location in our beam is prone to failure. Okay, so that ends our discussion on the application of influence diagram. So I hope that you have learned a lot, and please don't forget to subscribe to my channel. And guys, thank you for listening, and God bless.